Good evening, everyone. Physics is the soul of the universe. It describes everything from the tiniest to the largest, from quarks to black hole. But the subject itself is sometimes too technical. For example, some of us they don't like long, tedious equations, where someone other like my friend who he thinks that labs like having fun with friends. However, despite our personal likes and dislikes, the moment when your intuitions becomes parallel with your equations and experiments, you will feel the subject. Our department has a huge legacy of scientists from Professor C.V. Raman, Homi Bhabha, and Bikram Sarabhai to the great minds of Indian physics today. We have a host of cool professors who push the boundaries of our present understanding and sometimes bores with the course assignments. I can bet you $1 million that when you leave this hall today, you will have gained many insights into the bridges, the classical to the quantum world. That is exactly why we have gathered here today for this special lectures organized by the PDA committee. I thank everyone who has joined with us. The speaker for today is Sri Anil Ananthaswamy, known for building intuitions and by building science with philosophy and storytelling. He is also the author of several remarkable books, including The Man Who Wasn't There, Through Two Doors at Once. Now, this is what of many us already know, but that's not the end. It happens by the conspiracy of the universe that our speaker is a dear friend of one of our professor who wasn't hold back in letting his thoughts known to the world and has a great ability to solve huge Feynman integrals. Let me introduce you Professor B. Ananthanayan of CHP department to say a few words about your esteemed speaker.
And I'm so embarrassed, I don't know what I can say now. I'm just blushing. But luckily, because of my permanent tan, you're not going to be able to see it. So it's a great pleasure for me to be here. I've actually not stepped onto the stage in over 7 years, because the last time I took the stage, last time I took the stage was a day before I stepped down as chair of the CHEP after having served for over 9 years and 7 months. So it's a great pleasure to have Anil back here. So Anil gave a talk here at the faculty hall, I think, on one of his books, and the first time he came to IISc, I think, was in the year 2010 when he wrote his first book. So that day is really imprinted on us because we were still in the old building. And that's the day on which Apurva's scooter was stolen, which I'm sure that he remembers very distinctly, which is why you see him on his bicycle. They never recovered the scooter, but he did get a ticket for jumping a red light. So evidently, I don't know, this is how law enforcement works in our country. So thank you, PDA, for giving me this opportunity to speak about Anil and to welcome him back here. So you are a remarkable person, as our MC has already said. You are an award-winning science writer and a former staff writer and deputy news editor for the London-based New Scientist. But essentially, you're now self-employed and you do all this great work. So you wrote the first book, The Edge of Physics, a copy of which was owned by my late mother, and she very much enjoyed reading it again and again. and then you have written many more books. So we were together, as our MC pointed out, we were in the same hostel for over 3 years in IIT Madras more than 40 years ago. And we also had a year in common in the University of Delaware, where he had first joined for a master's in computer science, and then he moved on to the University of Washington in Seattle and went back to electrical engineering. He spent many years in industry, and then he discovered that his true calling was in science and in science writing. You've been doing a remarkable service to science, and you also do a lot of engaging with students. You run an annual science writing workshop at the NCBS in Bangalore. Anyway, let me also advertise that I'm giving a talk tomorrow at NCBS for the first time. Again, more divine conspiracy over here. So let me not take away your thunder, and I'd like to welcome you on behalf of IISc, of our departments, of PDA, and I'm sure we're going to have a thrilling 1 hour ahead of us. And do come again.
I will.
But we should give the gift afterwards. No?
Okay.
No, I'm just joking. You can give it right now.
Seriously?
Yeah, come. Yes.
All right.
Yeah.
So then I can just leave, because now that I've got the
Yes.
gift, what am I doing it? Yeah, thank you.
Yeah, here's one. Yeah.
Small gift, and we have a small community of students.
Oh, well, thank you very much. This is lovely. Let me just keep this. So you keep it for me, yeah? Okay. Thank you. Thank you, Ananth, for that lovely introduction. And I have to figure out now what you've done to my machine. Quit or continue? Quit. Okay. So it's a pleasure to be back here at IISc. I think the very first talk I gave about one of my books, very first talks ever, was 2 months before The Edge of Physics was published. And that was at CHAP in the old building, I think, right? And I remember it was a particularly frightening time for me, because I had just transitioned to being a science writer. I had written this book, and the first talk was to an audience of physicists, and it went reasonably well, I thought, at that. But yeah, so those memories are there, and it's been quite nice to come back every time and give a talk. So thank you for being here. I'm assuming that there are people in this audience who are not physicists. If you're all physicists, then we can just go home now, because you'll know almost everything that I have to say. But with the assumption that some of you may not know some of the physics that I'm going to talk about. So bear with me for those of you who know the physics, because it's going to be fairly trivial for you. And maybe then for those of you who know the physics, just view this as how a writer might approach the subject of trying to explain something that is complex to a lay audience. So you can put that meta hat on and look at it as an exercise in storytelling. But there is physics in this. So for people who are not familiar with the physics, and hopefully this will have something to contribute. Let me start with, so the other thing I wanted to say, I haven't been well the last few days, so basically been lying in bed and not speaking, not doing anything, so my voice is kind of, I just don't feel like I want to speak, so this is going to feel very weird for me. So if I occasionally kind of drift off, it's because of that. So let me start by telling you a little bit about just how weird quantum mechanics is. This was the topic of my book, Through Two Doors at Once, which was essentially the story of quantum mechanics told through the lens of a single experiment, the double-slit experiment. And most of you, even if you're not physicists, would have heard of this one experiment in particular, especially if you read popular science, because it's a very well-used experiment in popular science circles, and also highly abused, because it lends itself to all sorts of interpretations, and people can make all sorts of claims about the nature of reality based on this one experiment. But let me just give you a sense for what it is. So the double-slit experiment essentially is, you take a source of light, monochromatic light, at a single frequency. Let's say you have a laser pointer with that is shooting out red laser light, a beam of light, and you shine it at a screen, opaque screen, into which are cut two very fine slits, right? And the question you're asked is, what will you see on the other side if you have let's say a photographic plate that is recording whatever light is passing through the two slits, right? A naive classically attuned meaning a mind that is attuned to the goings on of the classical everyday world, is going to potentially say that, I'm going to see two strips of light because light would have gone through the two slits, and on the other side I should see just two strips of light. Light doesn't behave like that, classical light. You end up seeing a pattern of dark and light bands. So on the screen that you're seeing, think of the screen that you're seeing where the light is landing as a negative of a photographic plate, right? So the dark bands are where most of the light is hitting, and the white portions are where there's no light, right? So you're essentially getting these bands of light and dark and light and dark. And that's an interference pattern, and this was something that was first done, a version of this was first done by Thomas Young back in the early 1800s, and this went a long way towards proving that light behaves like a wave, right? So this is well before quantum mechanics, early 1800s. And remember that before this, the nature of light was a point of debate, and the view that had held forth until then was Newton's ideas that light was made of corpuscles or particles, right? So, but when this experiment was done, everyone got convinced that, okay, light is wave-like in nature, and this, you could do this at home with a carefully set up experiment. This is not very difficult to do. Now, I want to just change this a little bit. Imagine you're able to take that same laser light and somehow turn down the intensity of the light that's coming out. Of course, you can't do that using your regular standard laser pointer, but assume that you can somehow turn it down so that eventually you're getting a single particle of light. We'll come to why we should even think about particles of light, but assume that you are able to turn down the intensity so much that eventually you're just getting one particle of light at a time, and you're also able to guarantee that there is only one particle of light that is in motion from the moment it leaves the laser pointer and to the time it goes and hits the detector, right? So there's, in the experiment, at any given time, there's only one particle of light that's traveling. Now you're asked, what are you going to see? Now this is like you're shooting bullets at the screen. The bullets are very small, of a size that can potentially go through the slit. So the question is, what will you see on the other side, right? So amongst the people who are not physicists here, what do you think? How many are non-physicists here? Thank you. That's a fair bunch. And what do you think might be intuitively your sense for what might happen on the other side, right? Remember, that's a photographic plate, so that plate is recording one particle of light that's hitting, right? So intuitively, well, let me just jump the gun here and say, let's start with this, right? Let's close one of the slits. Now you do the same thing. You're shooting one particle at a time, and if there's a photographic plate on the other side, you are going to see something like that. You're going to see particles of light lined up it won't be as narrow as that, but still you'll get a distribution that looks more or less like that. If I were to close the left slit, then you would get the pattern shifted a little bit towards the right slit, right? You're going to get these two. So my intuition tells me that if I were to open both, I should see something like that, right? And of course, we're talking about quantum mechanics. Nothing is as expected. So what happens is that instead of those two slits, you again get an interference pattern, right? Now remember that an interference pattern happens because, let me just go back to this first slide here. This is explained because this is classical light, which means light that you would get from, like if I had a laser pointer, right? So this is a laser pointer, right? The light that is hitting is a beam of light, and even though you don't see it on the way there, but these are not single photons going there. And this you can treat like a wave, and when a wave hits those two slits, it essentially diffracts off of each slit and then starts propagating on the other side. These waves interact, and what you get on the other side is called an interference pattern. It's a wave. It's a phenomena that is only possible if a wave is propagating through the two slits, right? But we have now started saying that there is no wave that we are sending. We are sending single particles of light, right? And we are asking the question, why do you get this pattern when we know that that pattern comes about only when a wave goes through the two slits, right? So the top is showing you what happens when a wave goes through it. On the bottom, we are showing the same pattern that appears over time, right? Even though you're sending one particle at a time. So what is it that is behaving like a wave and going through both slits and causing that interference pattern, right? Remember, and so we'll come to why this is actually quite a interesting mystery, but this is the beginning of the weirdness of quantum mechanics. Even trying to make sense of why this experiment behaves the way it does leads us to very, very interesting questions. So let's not, I'm just keep all that in mind, and I want to sort of give you a brief look at how we even came to this point in the history of physics. So let's go back to the birth of quantum mechanics. So in 1900s, Max Planck shows that there are certain idealized objects in physics called black bodies. And there was a discrepancy between what theory and experiments, what theory was saying and what experiments were showing at the time. And so Max Planck was able to reconcile this discrepancy by proposing that black bodies must absorb or emit radiation in discrete, indivisible chunks or quanta of energy. Until then, energy was considered infinitely divisible, which means you could keep breaking down, the idea that you could take a piece of matter and keep breaking it down into smaller and smaller chunks. With matter, we know that at least at the time, that there was some limit to how small you could make it, but with energy, people thought that, it was infinitely divisible. And it turned out that when Max Planck came up with his ideas, he basically pointed out that you cannot do that with energy either, and any given frequency of energy has to have a quantum beyond which you cannot break it down, right? So that was the beginning of this idea of quantization of energy. 1905, Einstein argues that light too must come in indivisible quanta, right? So he uses this idea of arguing that light must be made of indivisible quanta, and these quanta came to be called photons. He used that to explain the photoelectric effect, right? And I don't know if you know that Einstein never got a Nobel for his theories of special and general relativity. He got a Nobel for the photoelectric effect. And what was interesting was that Max Planck, when he recommends Einstein for, I think it was the Prussian Academy of Sciences, he never liked the fact that Einstein was arguing that light comes in photons. Light is composed of photons. He basically, his recommendation to the Prussian Academy of Sciences was, this is an amazing physicist, except that he has made this idiotic suggestion that light, is composed of quanta too, so you must not hold it against him, and you still should make him a member of the Prussian Academy of Sciences. So Planck wasn't particularly pleased with Einstein's suggestion that photons were the indivisible components of light, right? So these things were happening kind of, piecemeal. 1913, Niels Bohr argues that electrons that are orbiting the nucleus of an atom can also only be in discrete energy states. So this is what leads to the observations that atoms, when they absorb or emit radiation, they do it in sort of in very discrete fashion. You don't get this continuous spectrum, and they had lots of difficulty explaining why atoms are stable, etc., etc. If you use the old versions of old ways of thinking about how what an atom was. So Niels Bohr's argument that electrons are orbiting the nucleus of an atom in discrete energy states, all these things were happening. These were the beginnings of the idea that energy was quantized, and then at least in the case of light, that light could exhibit both wave nature and particle nature, because particle nature was becoming evident because of Einstein's work with photoelectric effect. The wave nature was already established with electromagnetic theory and Young's double slit, etc. And then the idea that energy cannot be infinitely subdivided into ever smaller chunks. There is a smallest unit of energy for each frequency of electromagnetic radiation, right? So red light will have a certain small chunk, green light will have a different chunk, etc., right? So these were fundamental ideas that were taking root, and then the formalization of quantum mechanics happens in the 20s. Louis de Broglie develops the wave-particle duality for matter, just like Einstein had done for the photon. Heisenberg comes up with matrix mechanics, which is a particular way of describing how a quantum system, such as an electron, would behave in the presence of external forces. And then very soon after that, Schrödinger develops something called wave mechanics, so if you take a electron and you want to describe its quantum state, you would describe it using this state called psi, or what I've written out there. Let's see. The symbol that you see out there, it's also called the wave function, and Schrödinger showed how the quantum state would evolve over time using a differential equation, which came to be called the Schrödinger equation. So all these things were happening, and these were ways of then figuring out the dynamics of quantum mechanical systems. And in 1926, Schrödinger himself shows that wave mechanics and matrix mechanics are basically equivalent. They're just different formulations of the same thing, except that Schrödinger is very convinced that he is talking about something very physical when he's describing the quantum state of a system using the wave function and describing the evolution of the wave function. He thinks at this time, at least in 1926, that he has found something that is a physical description, but it's really unclear, right? So Schrödinger believes that the wave function represents, for example, the smeared out physical distribution of an electron as it's moving or as it's evolving. The same year, Max Born shows that psi, the wave function, doesn't represent a physical wave, right? But rather, the square of the wave function's amplitude gives you so this is a whole bunch of words here, so let me just go through it slowly. It gives you the probability density of finding an electron or particle at some location if you choose to measure it there, right? So it's not telling you that the electron is here, it's essentially just giving you a way to calculate the probability of finding it there if you were to look for it there, right? And this is true of whatever you choose to sort of look at in terms of the quantum state of a system. So given that this is what quantum mechanics is telling us by 1926, then we come back to this question. So what's going through both slits, right? We have this scenario here. Something wave-like is going through both the slits. It is interacting and creating this pattern on the other side. But remember, we are shooting individual particles of light now, right? We are taking, let's say, a photon of red light, one at a time, right? Let's say 10,000 photons, one every second, and there's a photographic plate that is recording the photons as they land on the other side. What is, the thing that describes the state of the individual photon is the wave function of that single photon. And it's that wave function that hits the two slits. So mathematically, what you are able to show is that it's the wave function that hits the two slits. It's the wave function that spreads out on the other side, interferes with itself, or the two states of the wave function interfere, right? and you get that interference pattern. That interference pattern is basically what you would get if you asked, if I choose to look for a single photon on that side where the photographic plate is, what is the probability that I'll find it there? So for any given single photon, you can only talk in terms of probabilities, right? You cannot say where any given single photon will go with certainty. You can only say, oh, there's a 30% chance it will end up on one of these strips. There is 0% chance it will go somewhere. Well, there's never a 0% chance, but let's say, that you are talking in terms of probabilities, and those probabilities, it turns out, they will be borne out, no pun intended to Max Born, they will be borne out if you, I really didn't mean that pun. Those probabilities will turn out to be correct if you did this 10,000 times, and you will see that, that's where the electrons or the photon will end up. And so the wave function is going through the slits, but what is the wave function, right? And this is essentially at the heart of this question about the theme of this talk, which is this question about, is there a divide between the quantum world and the classical world? So for us, for most part, unless you're a quantum physicist sitting in a quantum experiment lab, you're unlikely to experience anything that is quantum mechanical. We definitely don't experience it in terms of our senses, in terms of their experiments. You might, if you're doing those kinds of experiments, but for most of us, the everyday experience of the world is completely classical. But it's also clear from the physics that the smallest components of matter energy, like photons, electrons, neutrons, even atoms, behave according to the laws of quantum mechanics, right? So the theory definitely, by this time, 1920s, 1930s, 1940s, it was very clear that it held true for the smallest. But what about something larger than that? So where does the theory that describes the behavior of the very small, right, stop being effective? Where does say Einstein's general relativity take over for describing, or Newtonian physics take over for describing things that are larger than a certain size, right? And this was not just a philosophical question, even though it seems like that sometimes, especially when Niels Bohr is arguing. So Niels Bohr, when he came up with the Copenhagen interpretation, he argued for an operational definition of this quantum classical divide. He basically said that any apparatus making measurements of a quantum system is by definition a classical system, and the thing that is being measured, as long as it's behaving quantum mechanically, is the quantum system, right? So the thing that is being measured or observed is the thing that is quantum mechanical, and the thing that is doing the measurement or doing the observing is classical. But it left open the actual notion of a divide completely open. You could basically put that quantum classical cut anywhere you wanted based on your measurement apparatus, and this idea would still hold. So there was no formal way of specifying what one really meant by saying this system can be described by classical physics and this system is described by quantum physics, right? The other thing that happens in the Copenhagen interpretation is that, so let me just go back to the, so here, right, if you think of this wave that I'm depicting here as the wave function, the mathematical wave function representing a single photon, right, and it's propagating through the two slits, and there is a measurement that is happening at the site of the photographic plate. The photographic plate is doing a measurement of the photon to find the photon, basically. So any given photon will end up in one of those black strips, right? So until the measurement is actually made by the photographic plate, the photon has a non-zero probability of being in multiple places, right? It's only when the measurement is done that the photon ends up in one of those possible places. So the Copenhagen interpretation says that the wave function keeps propagating in this case, and when it hits the photographic plate, it collapses, right? There is this idea called the collapse of the wave function, and the collapse is very much a property of measurement. So it's when you do a measurement that you cause the wave function to collapse. So until then, the wave function of the photon is spread out, which means that the photon can be in many likely places, and if with different probabilities, and it's when you measure it, it suddenly ends up in one place. Suddenly, well, at the moment you make the measurement, and the wave function technically just collapses and has a peak at one point and zero everywhere else, and then again it'll start evolving if the system allows it to, right? So the collapse of the wave function is a very big idea in the Copenhagen interpretation. And the central sort of culprit here is the measurement apparatus, right? The measurement apparatus is the one causing the collapse, right? Now, so what this means is that if you think about it a little bit, and there are very interesting experiments that you can do, which suggest that until you make a measurement, until you make an observation of reality, in this case, the reality of meaning where the photon is, you can say nothing concrete about the photon. You cannot say anything about where the photon actually is, right? You cannot even talk about an actual trajectory that the photon is taking. A single photon, there is no precise trajectory that you can draw from the laser pointer to the screen because there is no way of, in the Copenhagen interpretation, there is no way of actually charting that. Like if I chuck the ball from here to there, Newtonian mechanics will tell me exactly how to calculate the trajectory from the moment the ball leaves my hand all the way to when somebody catches it, right? I can predict that in advance. I can completely chart that. You can't do that for a quantum particle. So, okay, for Arindam, you've already heard this talk, so you can't say anything. All right. So the collapse is a huge issue, which basically is arguing that the act of measurement is causing the collapse, and the act of measurement is creating reality, right? So this is very disturbing to other ways of thinking about what it means to have a reality and what it means to do physics. For instance, there are plenty of physicists who decry the role of measurement or observer, quote unquote, in determining the state of the quantum system, right? They would rather that the state of the quantum system existed independently of the observer, and whatever measurement we did or whatever observation we did just discovers that reality, right? So, but it's also true, if you look at the math of quantum mechanics, that the wave functions do propagate and wave functions do spread out, and that there is this notion of a wave function being very spread out, but at the moment of measurement, you find that the electron or photon or whatever it is you're choosing to do with the quantum system is in one of those possible states. It's not in all of them, it is in one of those states. And so obviously that part is happening. The question is, was the electron there and you just found it there? Or did the act of measurement cause the electron to appear there, right? So if the electron had already appeared, had been there, and your measurement just discovered it, it implies that the wave function did propagate and something else caused it to collapse, and you're discovering the effects of the collapse upon measurement, right? So there are these theories called collapse theories, which essentially argue for that way of thinking about reality, which is basically saying that the wave function is sort of evolving and it stochastically collapses. There are various ways in which mathematically you can make it collapse, and then the act of measurement just discovers the outcome of the collapse. So we are not creating reality by making measurements, we are observing an objective reality that already exists, even though the reality itself might be still stochastic, right? So, but what is very, very interesting with collapse theories is that this implies a quantum classical divide, because almost all of these collapse theories, there are many versions of them. Many versions, including one by Roger Penrose, which is something called a gravitational collapse theory, where he invokes sort of the role of gravity in causing collapse. That as quantum systems get more and more massive, he has a very hand-wavy theory about this. It's not a very precise formulation. He says that basically if you had a mass here which was in superposition of being in one location and another location, and we know that from Einstein's relativity that mass warps space-time, and so if you had a mass that was in superposition of being in this position and this position, you would have two configurations of space-time that are in superposition, and his argument is that that is an unstable configuration for space-time if the mass becomes too big, right? So it will eventually collapse into one or the other, and he uses that as a way to argue that collapse is constantly happening and we are just discovering the effects of that. But in collapse theories, one of the implicit sort of things that comes out of this is that there is a quantum classical divide, because collapse happens because the mass of the system exceeds a certain mass range, and then that speeds up the collapse. So a photon might remain in a superposition of states. A superposition of states simply means that, like when you looked at the double slit, the photon was in a superposition of having gone through the left slit and the right slit, and it remained in that state until the measurement was made, right? So a photon will technically, if the environment lets it be, will remain in that superposition for a long, long time. Whereas something very large, according to these collapse theories, will collapse much, much faster. And so now suddenly we have a handle on the quantum classical divide, right? We can basically start saying, okay, if these collapse theories are true, then we should be able to kind of test this. We should be able to, for instance, start sending bigger and bigger things through double slits to see when the interference pattern disappears. When do the patterns on the other side of the screen start looking like as if classical particles are going through, right? Where you just see two strips of light as opposed to this interference pattern, right? So, but I also want to mention this. There is nothing in standard quantum theory that suggests that there is a quantum classical divide. According to standard quantum theory, the way it's used in textbooks and probably still taught in this manner, is that this theory might be universally applicable. There's nothing in the theory that says, okay, this is where it ends being applicable to objects. Anything larger than this should be classical. Anything smaller than this should be quantum, right? Nothing is there. The collapse theories I was talking about are kind of add-ons to the standard quantum theory. So people started then trying to do double slit experiments with larger things, right? So by the 1960s, they had already done it with electrons. I think neutrons were already tested out. I forget what the largest molecules in the 60s were, but things had, people had come to a point where now, by the 90s, they started showing that, particularly Anton Zeilinger's group in Vienna, they were effectively showing that you could do double slit experiments with these C60 molecules containing 60 carbon atoms. It's a massive molecules for the time that you could send through the double slits and still observe the interference pattern on the other side. So, and again, individual sort of C60 molecules being sent through the double slit, and these things are behaving quantum mechanically. They are behaving as if they are going through both slits at once, right? And interfering on the other side to create the interference pattern. Then there was a student of Anton Zeilinger called Marcus Arndt, who then went on to make this his really a sort of career out of sort of studying this aspect of quantum mechanics, where he showed that you can get interference from molecules in 2012 with about 1,300 atomic mass units, molecules of that size going through the double slit, and you're still getting interference. 2013, he upped it to 10,000 atomic mass units, and the last I looked at in 2019, he had managed to show interference for molecules with 25,000 atomic mass units. So really massive molecules going through double slits and still getting interference patterns, right? And I think I have a video here. Okay, great. I don't see. I'm not sure why the video is not playing. All right, I'm not sure why this is not playing. If I can figure it out later, I'll come back to it. But basically, this is a lovely video that I can send you the link. You can watch it on YouTube. It's basically recordings of a fluorescence, a molecule stacked with a fluorescent marker where you can see it lighting up as it lands on the far screen. And over time, you can see the interference pattern appearing. And these are really, really large molecules. So it's very clear that as far as the double slit experiment is concerned, these experiments have been done with larger and larger molecules, and whatever system that they're able to do this with, it is still displaying quantum mechanical properties, which means that they still haven't found at least the kind of limits that the collapse theories had suggested were already sort of disproven. Collapse theories are funny in that when an experiment says that your theory is wrong, they can just tweak a couple of parameters and move the mass scale a little further down. So that's what's happening. Unsatisfactory, but it's still a valid theory. And to be fair to collapse theories, they are the only ones who make any kind of sort of empirical predictions about this issue. But for instance, there is the multiverse, which says there is sorry. I won't be able to tell you off the top of my head, but it's very much dependent on the wavelength that you're talking of. Very, very fine slits, right? Some physicists here can give you, Arindam, would you know? If you had a photon, what would be the width of the slit?
About half a micrometer.
Half a micrometer, yeah. But yeah, it depends on the wavelength of whatever it is that you are.
Smaller than 0.
Yeah. Yeah, correspondingly they'll get bigger, but yeah. Yes, everything, absolutely, yeah, the whole system. Okay, so all this was to say that people were thinking about the quantum classical divide, right? And they've been trying to do experiments with bigger and bigger quantum systems. I can actually tell you a little anecdote about visiting a researcher at UC Santa Barbara, Dirk Baumeister, who was doing an experiment with a tabletop version of the double slit experiment using something called a Mach-Zehnder interferometer. He was trying to test Penrose's gravitational collapse theory. So Penrose's gravitational collapse theory was suggesting that, after certain mass scales, you should stop seeing the interference pattern because the system is not quantum mechanical anymore. And the way Baumeister was trying to, I don't know if I'm saying his name right, I think it's Baumeister. What he had done was he had managed to create, so if you know a Mach-Zehnder interferometer, it involves sending light along two paths and they are bounced off mirrors, and he had managed to create mirrors that he could put in superposition of being in multiple positions, right? So mirrors themselves were in superposition of being in this position or that position, and hence you could see the effect of that in the interference pattern. And the idea was that if the mirrors became so big enough, then suddenly they should collapse to being in only one state, and the interference pattern should disappear, right? So Baumeister was doing these experiments in order to test Penrose's theory. But even as he was doing the experiment, I remember him telling me, I don't believe we will find the quantum classical divide. So here was an experimentalist who was building these amazing experiments, but was also completely convinced that he's not going to see anything, because he was convinced that there is no such divide, right? So the effort to do these experiments with bigger and bigger quantum systems has always been there, like to try and figure out if really there is some sort of divide that can make it very clear as to what is happening. This brings us to quantum tunneling, which is another way of trying to come at the same problem, and we have to go back in history again. So back to 1927. This is somebody called a German physicist called Friedrich Hund, who identifies this phenomenon called quantum tunneling, which was the one that won the 2025 Nobel Prize. We'll come to that in a bit. So he was the first to show that wave functions, that thing that we saw propagating through the two slits, the wave function describes the quantum state of a quantum system. And he was the first to show that these things can pass through what are otherwise considered impenetrable barriers, right? So, impenetrable energy barrier for a classical system, wave function can sometimes pass through that. And when a wave function passes through something, in the sense that it spreads through space and time and ends up on the other side of a barrier, technically, whatever that quantum system is, you could potentially find it on the other side of the barrier, right? So look at the figure below, which I've stolen from the Nobel Committee's website with due attribution at the bottom. So if you were chucking a ball at a wall, right, there is no way that ball will ever cross on to the other side. Right? If in the classical world. In the quantum world, something like that might happen, which is shown on the right-hand side. That occasionally when you chuck the ball, you will find it on the other side. Even though classically speaking, there is an impenetrable barrier, in this case a wall. But when you're talking of quantum systems and energies, think of that wall as some kind of energy barrier. And there will be times when that quantum system will end up on the other side, right? So Kuhn was the first to really thoroughly show that this phenomenon is possible, and in fact he explained the inversion of the ammonia molecule. So the ammonia molecule has I think it's a pyramidal structure where you have the 3 hydrogen atoms in a plane, and then there's the nitrogen atom at the peak of that pyramid, and the nitrogen atom can either be in the top or the bottom, and it will keep shuttling between the two. And it turns out that the way it does that is to if you just look at the energetics of the molecule, there is an energy barrier that classically the nitrogen atom shouldn't be able to penetrate and end up on the other side, but because of quantum tunneling it will keep doing that, right? So Hund explains that, and I forget, did he win the Nobel for this? I don't remember, because quantum tunneling has been a huge source for Nobel Prizes. I think he did, I forget. So this is the magic of LLMs. I could just prompt an LLM to give me code to run to show this effect. This is a wave function that is propagating, and there's an energy barrier, and the dotted line is telling you about the energy of the particle, and then the blue line is the wave function. Sorry, the square of the amplitude, right? And it's, in this case, it's just crashing against the barrier, and you see on the other side, nothing much is appearing in terms of the blue line, right? Now, if I were to just change the parameters a little bit, like make the energy barrier a little thinner and the particle energy a little bit more, then suddenly you start seeing that as the wave function hits the potential barrier, it spreads on the other side too. Right? There's a reflected part and there is a part that gets through, which means that there is a finite probability of the quantum system being on the other side. So occasionally you will find it on the other side, right? So, and again in 1928, Gamow uses quantum tunneling to explain alpha decay in radioactive nuclei. You all know this. An alpha particle is basically a helium-4 nucleus that sometimes tunnels through a potential barrier that surrounds the nucleus and ends up on the outside. And this is what leads to this form of radioactive decay. And until then, it was really hard to explain why nuclei are decaying like this. Why are they emitting alpha particles? And it turns out that quantum tunneling allows these alpha particles from within a heavy nucleus to just get out, and the material then gets transformed, right? So this was a big deal. And then some practical things started coming. Leo Isaki in 1957 discovers quantum tunneling in semiconductors. So, we all know about p-n junctions. So Isaki discovers that in a heavily doped p-n junction, his observation initially was that in a heavily doped p-n junction, the current decreases as the voltage across the junction increases, which was kind of counterintuitive. If you're increasing the current across some junction, you should be seeing if you're increasing the voltage voltage, you should be seeing the current increase. In this case, he was seeing the current drop, and then he figures out that it's because the current that you're normally seeing in the case of a heavily doped p-n junction is because of quantum tunneling. And as you're increasing the voltage, the electrons that are tunneling through are running out of states, to sort of tunnel through between the p-n junctions, and you're essentially turning off the quantum tunneling as you're increasing the voltage. So this was a big deal. We ended up with the tunneling diode, which is kind of a reverse of the regular diode, right? So this was a very practical application and became a huge thing in the semiconductor industry. And then, but one of the important things so far is that all of these things that we are talking of, they still remained in the microscopic realm, right? All of the quantum tunneling phenomena that we have talked about were still limited to particles that there was no dispute about whether these particles were governed by the laws of quantum mechanics, right? The idea was, the question from the perspective of the question we are asking about where is the quantum classical divide is that could this phenomenon be seen in more massive systems? So far, whether the stuff that, Isaki had seen in the tunneling diode situation, or the alpha particles here, or the Hund's work, all of this still applied to systems that were indisputably quantum mechanical, right? Now, no one was disputing that. Now, could quantum tunneling, for instance, now be seen in things that are much more massive? To answer that question, we need a little bit of a segue. So, pardon me, we have to go back to the discovery of superconductivity quickly. So in 1911, Heike Onnes sort of uses liquid helium at 4.1 Kelvin to cool mercury, and he discovers that when you cool mercury down to that temperature, the metal's electrical resistance vanishes, right? So this phenomenon, which eventually came to be called superconductivity, so he didn't win the Nobel for the phenomenon of superconductivity. He won the Nobel in 1913 for being the first to liquefy helium, cooling it down to 1.5 Kelvin, right? But this was the beginning of our understanding of superconductivity, right? A huge jump forward to many decades later, Bardeen, Cooper, and Schleifer proposed a microscopic theory of superconductivity. So in this BCS theory, they propose that the superconducting current is essentially what is called a superfluid of pairs of electrons, which are called Cooper pairs. Normally in a conducting material, you have individual electrons that are flowing that give us the current. In superconductivity, what happens is that these individual electrons pair up into these things called Cooper pairs. So individual electrons they go from being fermions to acting like bosons. The whole thing, all of the Cooper pairs taken together can be described by one quantum state. And this is a theoretical sort of explanation for what was happening in effects that had been discovered earlier. So this one wins a Nobel Prize in 1972 for a theory of superconductivity as to what might be happening here. Then Ivar, I'm trying to see if I can get his name right, Ivar Yevar, the G is silent. Ivar Yevar demonstrates that electrons then can tunnel through so if you have a thin insulating layer that separates two superconducting metal films, right, he shows that electrons from one side of the insulating layer can tunnel through that layer. So again, quantum mechanical tunneling, but in this case still just electrons. Brian Josephson in 1962 theoretically shows that Cooper pairs, those things that are responsible for superconductivity, can tunnel through a thin insulating layer that separates two superconductors. He receives the 1973 Nobel Prize along with Isaki for the tunnel diode discovery and Ivar Yevar. Right? So all of this thing is happening, and 63 again, Philip Anderson, John Rowell at Bell Labs demonstrate that the Josephson effect is real, and this is important because this leads us to the work that eventually got the 2025 Nobel Nobel Prize, yeah. So far, all of the experiments that have been done, the number of particles, the Cooper pairs tunneling to the insulating layers is still small. So the findings don't have much to say about the quantum classical divide. We're still talking of systems that are potentially still under the aegis of quantum theory. There's really no one is disputing that these things should behave quantum mechanically. So if they are tunneling, then whatever theories we have for quantum tunneling are enough to explain what's happening, right? So then there's work that happens in 1985 where John Clark, Michel Devoret, and John Martinez demonstrate that large number of Cooper pairs can tunnel through a barrier, an insulating layer. So they build a superconducting circuit that is 1 centimeter wide, right? Now suddenly we are in the realm of the macroscopic. This is really, really big relative to traditional quantum systems. The number of Cooper pairs that are tunneling through in the circuit are described by a single wave function. They make up one giant quantum object, and here's a depiction of what is happening, again taken from the Nobel Committee's website. So the top graphic shows you what normal electrons do inside a material. They're jostling with each other, and their interaction with each other and the material, that is what leads to electrical resistance, right? And normal conductors will behave like that. And then when you have a superconductor, you have those electrons all pairing up into these so-called Cooper pairs, and all those Cooper pairs taken together form one quantum object, right? And you describe the whole thing using one quantum state, and what is being shown there is basically a superconducting material with an insulating gap, which is the Josephson junction. And what the three researchers showed is that that particular quantum object made up of all those Cooper pairs can exist in two states. And in order to transition from one state to the another, which is made possible with so it can be in two states, and in order to transition from one state to the other, it has to kind of go through a potential barrier, right? And again, if you're classically minded, it won't be able to go through it, but they were able to show that if you had this system, then this one single huge quantum state would eventually tunnel from one to the other, and that would show up as a voltage across the Josephson junction, right? So basically, they showed that a very, very large system made of billions of Cooper pairs could tunnel through a potential barrier, and suddenly we're in the realm of the macroscopic, right? And so the quantum object, in this case, all of the Cooper pairs taken together, can exist in one of two states. The lower energy state results in a zero voltage across that gap that we saw. The other higher energy state results in a voltage. So now they had a very precise way of measuring when the system was in one state and when the system was in the other state. And there is an energy barrier between those two states, and they showed a spontaneous tunneling effect that would happen between those two states. And this was happening even in the absence of any external energy input, right? And that's crucial. It was just spontaneously happening because of quantum tunneling, but now quantum tunneling being applied to what can technically be called something that is much, much larger in size than what came before, right? The other thing they also showed, they did more with the experiments in terms of energizing the system using microwaves and showing that the tunneling could be speeded up, and the energy, the system absorbed energies only at certain frequencies. So even there, the absorption of energy by the system was happening in a manner that was very reminiscent of quantization of energy. In fact, it is exactly that, right? So all of these things suddenly showed that this massive system was behaving quantum mechanically, and that is what led to their 2025 Nobel Prize, that it was formulated as sort of an experiment that showed that quantum mechanics is valid even at such large scales, right? So again, I've already talked about all this, that the superconducting circuit used by Clark, Devoret, and Martinez was a macroscopic object, and in earlier experiments that had been done before that, only a few Cooper pairs had tunneled through the insulating barriers, right? But here, in this particular experiment, there were billions that were tunneling through, and what this was showing, that if you had a quantum system that was suitably protected from the environment, right, you could still observe its quantum mechanical behavior. So there seems to be no sort of obvious quantum classical divide. Nothing so far, right? The quantum theory continues to hold true as long as the system that you're studying, if you're making it larger, you can somehow protect it from environmental disturbances and prevent it from, let's call it, collapsing into one or the other possible classical states, right? If you can keep it such that it can exist in a superposition of states, then it will show quantum mechanical behavior. It could be that there is tunneling between those states, or it could be that those states interfere with each other in the way it does in the double slit, and you get an interference pattern, etc. So all those effects can be observed. And there is, so far, no one has done an experiment which shows that, okay, this is where definitively quantum mechanics stops being applicable. So at this point, that's where we are. Right? This brings us to, quickly, as an aside, the net effect of all this is that this is partly why quantum computing is even possible, right? Quantum computing is essentially the idea that you can build quantum systems that are very large and that can be made to exist in a superposition of states for long enough to do a certain kind of computation, right? If there was a quantum classical divide, if systems could only be quantum mechanical up to a certain size and not beyond, then basically that puts a limit on the size of your quantum computer. But theoretically, we know, at least the people in the quantum computing community don't think that there is any such limit. And so they are continuing to dream up sort of quantum computers that are bigger and bigger in order to be able to do bigger and bigger calculations, right? So just a little bit of history here, because it's a pretty involved history and I'm taking a very tiny thread through that. So in 1999, Nakamura and colleagues developed the first superconducting quantum bit, or qubit, right? So the qubit is essentially a Josephson junction that separates a nanoscale superconducting island from a superconducting reservoir. This is all basically Cooper pairs, and they can control the number of Cooper pairs on the island with very great precision, right? And the number of Cooper pairs that are on the island dictates the state of the qubit. So they have a very fine way of controlling the qubit. And let me just tell you a little bit about what a qubit is. So in classical computing, bits can be either 0 or 1. In quantum computing, bits are in some superposition of 0 and 1, right? And so basically, mathematically, that's what it's saying. The qubit state is alpha times the state 0 plus beta times the state 1. And the probability that you will find the qubit to be 0 upon measurement is alpha square, and the probability that you will find it in state 1, sorry, have I... The probability, it's wrong out there. The probability that you'll find the qubit to be in state 1 is beta square, right? So qubit essentially is what is the building block of a quantum computing system. In classical computing, logic gates operate on bits. In quantum computing, logic gates operate on qubits, which can be in a superposition of states. And now, if the input to a quantum computer is in a superposition, then the output, as long as the entire quantum computer remains in superposition, the output will also be in an appropriate superposition. And this is the crucial aspect of what's happening in quantum computing. In classical computing, a Boolean circuit which is made by interconnecting a whole bunch of logic gates will deterministically produce an output given some input, right? So there's always a definite way to tell what a Boolean circuit will do in a classical computer given a certain input. We've all done truth tables, etc. in our engineering. So that's what it is. But in quantum computing, what happens is that because the entire circuit that you built from qubits as input qubits enter the system and the entire system evolves, the qubits start interacting with each other, they become entangled, and by the time you get to the output, you're in a situation where the entire output stage is in a superposition of many different states, and so you can argue that the path from the input to the output, the entire quantum computer has computed many different trajectories simultaneously. But then how do you get an eventual answer? The eventual answer still depends on you making a measurement, right? If you make a measurement now, instead of getting a deterministic answer, you can only talk probabilistically. The entire superposition that the quantum computer is in will collapse to one of the possible states that is in. So the design of the algorithm has to be such that it maximizes the collapse to the correct answer and minimizes that the collapse will happen to an erroneous answer. It can still collapse to provide an answer that is wrong, right? So designing a quantum computing algorithm is a very different ballgame compared to what you might do in classical computing. And this here is, I think, probably as quantum computers get bigger and bigger, is probably going to be the biggest demonstration of the fact that there is no quantum classical divide. Because if quantum computers continue to get bigger, and if we start making systems of 1,000 qubits or 2,000 and 10,000 qubits, we're essentially saying that we are not seeing any quantum classical divide, because these systems do exist in superposition for a long, long time, despite their size, and they do demonstrate quantum mechanical behavior, right? So, and potentially this is going to be the field from where you're going to get a lot more Nobel Prizes. One of them is going to be unambiguous demonstration of quantum supremacy. Quantum supremacy is the term that is used to argue for the fact that there will be things that quantum computers will be able to do in terms of their computation, which will be almost impossible in any finite length of time for a classical computer to do, right? So far, even though there have been claims of quantum supremacy, I think unambiguously not yet, right? Whatever has been done using the quantum computers that have been built so far, it has been possible to demonstrate the same thing being accomplished by classical computers in reasonable time, right? So it hasn't been unambiguous. So if somebody shows a problem being solved by a quantum computer that, let's say, would take 10,000 years for a classical computer to solve, Arindam is smiling, so he has something to say about it. So potentially there, area of much debate out there. Scalable quantum error correction, because quantum systems are so fragile, you need 1,000, approximately, in today's kind of technology, you need approximately 1,000 physical qubits in order to implement one logical qubit, right? Because of all the error correction that is needed, because these qubits keep losing their superposition. You can argue that means that there is a quantum classical divide, but that's not so. That argument doesn't quite work, because the whole system is evolving as one quantum system. So somebody who comes up with, so this is definitely not scalable. If you need to build, a quantum computer that has 1,000 logical qubits, you to have, 1,000 times more physical qubits in order to do that. That doesn't seem scalable. So anyone who comes up with a scalable quantum error correction method will probably be in for a big Nobel. Of course, anyone who comes up with the first useful large-scale quantum computer, which is related to the above two, and then of course the algorithms themselves, right? It's very, very difficult to design algorithms that work on. So not all problems can be tackled by quantum computers. And there are very specific kinds of problems that can be tackled, and the design of algorithms, like I mentioned earlier, has to be such that the algorithm kind of maximizes the likelihood that when you do make the measurement at the end, you maximize the probability of getting the right answer and you minimize the probability of getting the wrong answer, right? So all these things are possibly going to be areas where you are going to see a lot of effort going in. What does this tell us about the quantum classical divide? It's an open question. Nothing so far that I've told you says that there is one. And we honestly don't see any experiments or anything coming up that is going to clearly delineate the problem and say, okay, there is such a divide. The theories are not telling us. All the interpretations of quantum mechanics, except for collapse theories, which do provide you an empirical sort of testable hypothesis for where this divide might be, but every time somebody disproves them, they just move the boundary and say, okay, we just tweak one parameter and the boundary is pushed away a little further. Collapse theories, they were in the vogue. I don't know how much in fashion they are now, but they were in fashion a while ago, but they've kind of fallen out of favor. When it comes to interpreting what the math of quantum mechanics is telling about the true nature of reality, we are very far from a consensus, right? So if you try to break your head over what is happening in the double slit, is something actually going through the two slits? We definitely know mathematically what is going through the two slits. It's the wave function. But the wave function only tells you the probability of finding the particle of light or the electron or the atom or the molecule, whatever it is that you're sending through the double slit. It's only telling you the probability of finding that particle on the other side. Did the particle go through both slits? Obviously not, because especially when we talk of single particles of light, quantum mechanics says that that single particle of light cannot be subdivided any further, right? It is an indivisible unit of energy, so that energy cannot go through both slits. And so there are all these questions that come out when you try to answer physically what might be happening with that. If you assume that the wave function is itself something real, even though, yes, we talk of it mathematically, but if it is also something real, that is something ontological about the world, then that creates other headaches, right? The moment you assume that the wave function is something real that goes through both slits, there are other things that end up causing problems with, and this is exactly the thing that Einstein used to worry about with in terms of the consequences of quantum mechanics, is that it has, it then comes in conflict with things that he would have preferred in a theory. So whether you think the wave function is real, or whether you think it is just representing something about our knowledge of the physical world, no matter what approach you take as to explaining what goes through the two slits, you end up with problems on the other side. And nothing is without a sort of headaches. So right now, all bets are on the table as to what might be happening in terms of the interpretations of the mathematics of quantum mechanics, which also means that all bets are on the table as to the quantum classical divide. But if you talk to quantum physicists, most of them are going to say that there is probably no such divide. But we still have to explain then, why is the observable world in our everyday experience classical and not quantum mechanical? So those questions remain. I'm not going to answer any of them right now, so I'll just leave it there because I don't have answers. So I'll stop here, and thank you. My sincere apologies. My voice is absolutely not okay.
We can have a quick couple of questions if anybody has. Yeah.
Talk was okay.
Yeah, I was running out of breath every 3 sentences. I could feel myself like having.
I'm a physicist. I'm old, but I still enjoyed a lot your seminar. I would like to go back to the. You made a simple remark about Planck and Einstein.
Yeah.
I think this is. I didn't know about this, but I knew something, that this is a long-standing problem, because the century before, which I think belonged more Planck, came to a beautiful conclusion that a previous long-standing fight between Newton and Huygens, between corpuscular and wave understanding of electromagnetism found a solution in Maxwell. Okay? So finally, Maxwell says that electromagnetic is a wave theory. Then now comes quantum mechanics. Okay? This is a distraction of this fight, the solution of this fight. Okay? But people were still thinking that finally they found the solution between this duality, this problem. And now quantum mechanics says no, it's not this. So Planck somewhat belongs to the people who believed that of the previous century that Maxwell solved everything. But instead, Einstein, contrary to what people think, instead was already understanding that this was not the solution. I would like to say that my opinion, and I want your opinion on this, also that somebody's suicide is actually for this. Boltzmann.
Sorry, say that again?
Boltzmann suicided exactly for this, because he invented the statistical mechanics that is based on corpuscular theory, which was against the understanding of the period, okay? And so nobody gave credit to him at the moment. So if you want, what you came about to Planck and Einstein is a confirmation of my understanding of the previous century.
I think for me, Einstein represents a wonderful bridge between the previous century and what came later, right? He definitely, I mean, he gave birth to quantum mechanics, so he's very much a founder. But he also had serious reservations about the completeness of the theory, right? And in at least in popular science circles, there is this habit of saying, in stories about quantum mechanics, oh, Einstein was proven wrong and this and that. And if you actually look at how sort of the foundations of quantum mechanics has evolved, a lot of the evolution of our understanding of quantum mechanics is because of the kinds of objections that Einstein raised, and trying to understand and resolve those questions that he raised that have brought us to this point. So he very well understood exactly what the theory was about. He also saw what the problems were, which still remain, which haven't gone away. And I think he was amazing, and we definitely haven't proven him wrong or anything like that. So the debates between Bohr and Einstein notwithstanding, he just represents to me a fantastic bridge between two worlds.
The so-called witch path experiments,
Yeah.
double slit experiments, support the collapsing of the wave function theories?
So which path is simply this thing that I showed you earlier, right? If you go back to this, if you go back to the double slit, right? God, where did I go? Right, in this case, if you were to kind of say that I'm going to put a detector at one of the slits, because I'm sure that the photon has to go through this or that, let me just put a detector to see what happens. The moment you do that, the system starts behaving as if the photon is a particle, right? And this becomes much clearer when you do it in a Mach-Zehnder setup, which I haven't explained here, but yeah, essentially, if you do any which way measurement, the photons behave as if they're a particle, right? The probabilities that you get are more in tune with them being a particle, but it doesn't mean. The mathematics is very clear about what's happening, why that is happening. The question is more about, again, the role of measurement in this, right? The measurement is simply causing. Actually, I should have brought up it's much clearer if we look at the Mach-Zehnder set. In this setup, it's much harder to talk about the which way process. But no, it's not. It doesn't really prove collapse theory. Is that what you're asking? Does it prove collapse theories?
Yeah, I was wondering, the process of measurement itself, does it not lead to the collapse of the wave function?
So, but that's the Copenhagen argument, right? That the measurement is causing the collapse. You can, and the collapse theory is arguing that the collapse is happening stochastically because of whatever the system is, what the system state is in, and you are just discovering the effect of the collapse. Right? And you can explain the experiment with both theories. You can explain the empirical outcomes of the double slit experiment using collapse theories, using the Copenhagen interpretation, and there's no way to empirically separate them at the scale of the mass scale of the photon, right? It's true that the collapse theories will say that as the thing that is going through both slits starts getting bigger and bigger, then you will definitely see a collapse. Right? And then the interference pattern will start changing in very predictable ways if the underlying theory is actually the collapse theory and not something else. And we haven't seen that yet. Right? So both things still hold, because the collapse theory parameters can be changed to accommodate the fact that it is still valid in whatever regime you are making the measurements. And so both things are still valid right now. In fact, you can explain this using Bohmian mechanics, which has a completely different notion of what is going on. You can explain the outcomes of the double slit using many worlds interpretations, just about any interpretation of quantum mechanics you want to bring into the picture. You can explain the probabilities that you need to explain using those interpretations. So empirically, they are unable to separate themselves out and say that we are making the correct prediction. They all make the same prediction. In fact, that is the problem with these interpretations. They have to be sort of engineered or created in order to explain existing observations. Because if they don't do that, then they are already out of running. But because they work so hard at creating theories that explain the existing observations, they don't separate themselves out. Even though the underlying physical reality that they are positing, they are very different from each other. Whether the reality exists independent of measurement in the case of Bohmian mechanics or collapse theories, or whether reality is created because of measurement by according to the Copenhagen interpretation, we don't know. Yeah.
First of all, great talk, sir. I hope you get well soon.
Thank you.
So we have CPUs in our machines, we have graphical processing unit, GPUs in our machines.
Yeah.
Do you think we'll have QPUs in our machines? And if yes, when? What's your take on
Oh God, I have no idea. I don't even know how to project the trajectory of these GPUs now, because they are doing my head in. There are experts here. You can, like, one guy sitting right in front of you. You can ask Professor Arindam. He would know. Arindam, you have.
No, well, we already have QPU. It's just that in a cloud, in the sense, somebody in IBM will do it.
Sorry to interrupt you, sir. Commercially available device, in commercially available.
That is a long.
You can buy the
But of the size of current GPUs, that's a long way off. We don't have commercially available, off-the-shelf, small quantum computers that you can just plug in and play with. No.
We don't.
I mean, have you looked at the setup needed to run a quantum computer? There's no way we're coming there.
Hello, sir. So my question is related to, like, if we view photon as the quantum of electromagnetic field, does that mean there has to be some minimum field strength required for it to propagate? And like in vacuum, the light speed is governed, like it is decided by the permeability and permittivity. So, like, how does it constrain? How can we?
You are making me think now of my electrical engineering, which I have long forgotten. You have professors here. Okay, this is for you. Permissivity, remember we studied all this. I really won't be able to answer that off the top of my head. I have moved away so far into conceptual things and not into the details of these things. Arindam?
I think you answered the question.
if we view the photon as a quantum of electromagnetic field, then
Which it is,
yeah, it is. So that means there is some minimum possible energy, the electric field strength that has to be there for the light to propagate, and it propagates in vacuum at a constant speed, which is decided by permeability and permittivity of vacuum. So why is that? How is
I mean, I think at the end of the day, a photon is a quantity of energy. So, and that energy is given by the wavelength and the Planck's constant or frequency. So that moves like an electromagnetic field, and it can move through vacuum. In the vacuum, its speed is the highest, which is the speed of light. Now the question is, why is that? Is something which
I don't think we have a in principle answer to that. No, we don't. So you're asking
any directions to think about it more?
I don't know. Start reading textbooks, I guess. That I'm not sure what else I can tell you. There's no single source of an answer for that. It's basically you're asking a very foundational question, and that particular question is in principle not been answered.
Thank you, sir.
Please don't ask me questions that may remind me of my electrical engineering days. That's all.
Hello, sir.
Yeah.
So you talked about collapse theories,
Yeah.
and you said that there are two ways to think about wave function collapse, and one of those things is that the wave function collapses not because of the measurement, that before you do the measurement something happens and one of the state is appearing. This reminds me a lot of the hidden variable theory. So is there a connection between this and that?
No, I mean, never say no with quantum mechanics, but as far as I know, collapse theories just posit that collapse is just stochastic. There is a parameter that governs that, and it's a completely stochastic thing. There is no underlying mechanism that is posited in the traditional collapse theory. So I'm talking of these things called GRW theories, right? So, which is actually why I was quite why I quite liked Penrose's gravitational collapse theory, even though it is less formalized and quite hand-wavy in terms of what is happening. But he actually says that there is a mechanistic reason for why the collapse happens, right? Because a mass that is in superposition of being in two places ends up warping space-time, and there are two configurations of space-time now that are in superposition, and he calls that as an unstable state, and then he posits that when that instability reaches a certain amount, it will collapse. But it will again stochastically collapse to one of the possible states, right? So it's not like there's a clear answer there either. But hidden variable theories are very different. They're actually positing a underlying reality that is not captured by the formalism of quantum mechanics. So what we are observing is kind of a projection of that underlying reality in standard quantum theory. And so like Bohmian mechanics would have a pilot wave that is guiding these particles, etc. Those are very different, right? And I don't see any connection between traditional collapse theories and hidden variable theories.
Thank you. So maybe this is a follow-up to what a friend had asked there about GPUs, and also I was wondering how, at least on the back of the envelope calculations, how hard is it to realize a full-scale quantum computer? I mean, we said that at this point, at least there are thousands of qubits implemented. So I don't know anything about quantum computing, but how difficult is it to implement maybe tens of thousands or millions of qubits of quantum computing power? Why is it so hard?
Because you have to preserve that entire thing in a quantum mechanical state, right? And so the basic problem with anything quantum mechanical is that any interaction with the environment will collapse that quantum state. And in order to do a quantum computation, you want to be able to propagate that entire superposition of states that your qubits are in, right? To evolve them to whatever sort of end state that you want them to get to, right? And if there is an interaction with the environment, then the whole thing will collapse midway, right? So, and this keeps happening, which is why for every logical qubit that you want to implement, you need anywhere from 50 to 100,000 physical qubits to keep doing error correction and maintain that whole thing as one logical qubit. So if you want to do 10,000, and if you want to build a large quantum computer with 1,000 logical qubits, you have to scale that up by whatever, 1,000, 10,000 times physical qubits. And that is an impossible size to keep in coherent superposition for any length of time. Because time is a factor here. You need a certain length of time for that quantum computation to proceed, right? So the longer the quantum computation, the longer you need to keep that whole thing in a coherent superposition. And that just becomes an enormous challenge. So technologically. So it's not something you can implement. I mean, there are chips now, but again, they're very small relative to the kind of things people are dreaming about. It'll probably happen. I just mentioned one kind of qubit, superconducting qubit. There are other kinds, which I don't know too much about, but there are other kinds that might be more amenable to sort of packaging in ways that avoid collapse.
Okay, so we will round up here.
Sure.
So thank you, Anil, for this talk.
Thank you. My pleasure. Thank you all for coming.
Applaud him once again, and thanks for everyone for coming.